Good morning, students. Uh, we start out the week with our springtime weather, and now we're getting the cool weather. I often call my relatives in Montana, and I tell them, I said, we started out with AC at the beginning of the week, and now we're using the heat again. So they laugh and think I'm crazy. I said, but no, that's just the nature of living in Texas and the Houston area near the water. They want more snow because they want to have plenty of people coming to Big Sky to ski and spend money. So I think it's very interesting that we have such a variety. And I still am perplexed by it, even though I've lived in this area for about 11 years. It's still every day a new day type thing. Now, what I want to do today is to make an effort, and I always like to look at the chat. Oh, good morning, everybody. This is great. It's like, what is it? Happy Thursday. I like the positive attitude. Wonderful. So just remember that a happy attitude is the beginning of a good day. And sometimes it's really hard to be positive. And just like you, I have to make the effort also. So thank you very much for the kind remarks. Okay, what I want to do today, ladies and gentlemen, is continue with the inequalities and absolute value concepts, and then move into the definition of a function. And so, again, the function material will be review, but again, I want to highlight some things that I think that are important that we should know in a pre-calculus class. Now, first off, what I want to do is just share my screen, go to the document cam, and I want to just go back to a result that I discussed last class. I did an inequality with the BVs, but remember we had a result called the conjunction. That is, we started out with a positive number C, then if we have some expression in X, we'll just call it X, less than C. I just want us to get a little bit better understanding of absolute value. Then this is equivalent to the compound inequality. That is, the additive inverse of C is less than X, which is less than C. So like I said before, you get this interval from negative C to C where X lives. If you say this. Now, when we do the double arrow here, that means these are equivalent. So this is equivalent to this and vice versa. If you have this, you can write this if you're solving an equation. And of course, if you have this is a nice symmetric interval about zero, you can go backwards. And I want to say more about that construct in a few minutes. But for instance, if we were just thinking of why this is true, there's several ways to go about this, but I want to make a comment that has to do with the BV technique that I think will make this a little bit easier. So remember, equivalently, if we start with the left-hand side, remember I told you there is a way to write the absolute value with the principal square root. That is, the principal square root is always non-negative. And so we can replace the absolute value with the square root of X squared. So if you ever write this, if you're doing a square root property type thing, and you've got to take the square root of something squared, the result is actually this. And so this is another means of writing the absolute value that can at many times be very useful to us. So we can go ahead and put the less than C. Now, if we had this equation in or inequality in a homework problem, we'd say, well, is this just like the equality, Professor Ron? Do we just square things? Well, what we have to do in this case is notice that we have an increasing inequality. That is, the square root of X squared is less than C. So what we can do is we can apply a function that's also increasing. That is, at this point, apply the square function, which is also increasing. Apply square function. So in essence, as long as the square function is an increasing function, it will preserve the so-called increasing inequality. So we can apply the square function, which says the square root of x squared squared will be less than c squared. But of course now, if we square the square root, that will relieve us of the radical. And we get x squared is less than c squared. Again, this is, we call the square function in this case inequality preserving, because we have an increasing inequality and we apply an increasing function, it preserves the inequality. That's really important. You will use that construct in calculus. And so now when we look at this, we're thinking, okay, well, this would be like the BB technique. So I'm trying to tie in the BB technique to this. And even though this is a little bit more intuitive, I think it will help you. So for instance, say you had to solve this where you were told that C was a positive number. And then you'd say, oh, okay, well, I need to get a 0. So the first thing we do is subtract C squared from both sides. And then you're like, okay, well, Professor Ron, you said at this point we need to find the BVs. When would this expression be 0? So we would factor it. This is just a difference of 2 squares. So we would have x minus c. Of course, you don't have to do this every time. I'm just giving you some idea as to why this is actually true, because a lot of times you get theorems in math and no one ever explains to you why they are working at all. And so you really don't develop any new ideas. It's like, well, I memorized it, but do I understand it? And so now when you look at this reminds us of what we did last class. And so you have the BVs, boundary values, and that'll be C and the additive inverse of C. So you're thinking, well, that's really taking us right here. So when you draw your number line, I thought about this when I got up this morning, and I thought, what would be a nice way to tie in the BV technique to this inequality in a way that the students might find it more appealing. And so that's what you all will do as future STEM professionals. Your boss will come in and say, well, I want you to come up with a way to solve this problem. We think we have an idea or solution, but it doesn't seem to always work. So I need you all to put your ideas together. So as STEM professionals, you'll be doing this, and it'll make the day less boring, I guess. So now when you look here, you're thinking, okay, well, we have the X, we'll just write the inequality or the actual factored part above the number line. And so here you're thinking, well, this is going to be positive on either end. So you could take a 0 here, and you could have like maybe a 2C here and a negative 2C here. Just thinking about test points, so to speak. So of course, if we look in the negative 2C, well, of course, when we put in the negative 2C here, we have a negative 3C. That's, of course, still negative. And then the negative 2C plus the C, that's still negative. So this is overall positive. Of course, if we put in the 0, then we get the negative C, that's less than 0. Again, because of the hypothesis on C. And then, of course, if we put in 0 here, that's just C, which is positive. So this is overall negative. Likewise, over here, we get the same thing as we got down here. The 2C here minus the C, that's just C, which is positive. And then the 2C plus the C, that's 3C. And of course, that's still positive. So now, when you look at what we have, we need less than 0. And so, of course, the equal to 0 is no good. That gets a 0. And of course, greater than 0, that's no good. So those get X's. And so in between here is where we get the plus. So what does that mean? Well, from the number line, this means that X lives between the additive inverse of C and C. Or, of course, if this is true, we can write this as a compound inequality, that is negative C less than X less than C. And so the idea is that we could reverse all of this. Lots of times when you do an equivalence, you do two directions, but sometimes you can phrase your argument in a way so that all the steps are reversible. And so we could just tie this argument and go backwards and get right back to here. So what I wanted to do was just give you some idea as to why we can replace this conjunction with the compound inequality. And hopefully this ties in the BV technique. Now, again, you don't, every time you do this, you don't have to do this argument or whatever. You don't even really need to think about it. But maybe now when you use this interpretation of this, you might say, well, I believe it. In the sense that you say, okay, in class, we went through an argument of this and I see how it ties into the BV technique. So in mathematics, like I've always said, you may work with a friend and they solve a problem a particular way and your technique's a little bit different. It doesn't matter. As long as you're both using good mathematics and you arrive at the finish line with a good result, then that's fine. So here's one way to think about the conjunction. So remember, this is what we call the conjunction. This construct right here with the absolute value is the conjunction. And then of course we have the disjunction, and that's important, but not certainly as important as this. Now, what I wanted to do before I do some more BV technique is I want to show you some little techniques about writing symmetric intervals. And I promised you that I would do this. So for instance, I've got a couple of examples here. So say we have the following interval. I'll just put EX for example. And so we have -2 to 8. And I want to just give you a way to think about this absolute value so it's not mysterious. So I would say write the interval using an inequality with absolute value. Now, of course, we could go ahead and do a compound inequality, kind of like what we have here, and just put X between -2 and 8, and that you're thinking, I'm done. Well, right, but it's not, it doesn't use the absolute value. So that's where the trick is. So we want to use the absolute value so that, of course, here's the idea. We know that we would have something like this. The real number X would live between -2 and 8. And then, of course, since we're including, we have the equal to. So these two expressions are the same. So how can we write this with the absolute value? Well, here's the technique to do it. The first thing I want you to do is find the midpoint of these two endpoints of the interval. So you can say MP. Again, from geometry, you just take the two numbers, -2 and 8, you add them and divide by 2. You basically take the average to get the point that's in between them. Again, this is just on the real number line, so the points are just singletons. So this gives you a 6 divided by 2, or a 3. So 3 is equidistant between -2 and 8 on the real number line. So that's the first part. And then what we want to do is we want to find the distance. So if we're right in between, if we're right in the dead center between -2 and 8, we want to know how much distance we can go to either side to meet those endpoints. So this is the second part. So we just do half the distance. So the distance between 8 or -2 and 8 will just be the right-hand endpoint minus the left-hand endpoint. And then, of course, we want half of it because we already know the 3 is halfway in between. So we take the distance and we divide by 2. So this gives us 10 over 2, which is 5. Now remember, when we do Euclidean distance, we'll have ordered pairs and we'll use right triangles. So that'll be a whole lot more complicated. But when we're on the number line, if you want the distance between two uh, uh, points on the number line, you just take the right endpoint minus the left. And then in this case, we want half of it. So we divide by 2. So now this implies that we take our center point, absolute value, x minus 3, and then we can move 5 units on either side of 3. And that's where this goes, right there. So now this inequality with absolute value is, and of course we can be equal to, so I've got the brackets. So of course, let me be sure to have the equal to. So now notice this is equivalent to this. Now we knew this from the very beginning, but now we have what we call a symmetric inequality. We have an interval that's symmetric about 3. And in calculus, that is really important because, ladies and gentlemen, say we were doing a limit as x approaches 3. We need to approach 3 from either side in a nice symmetric interval. That is a construct in calculus that is very important. And unfortunately, in pre-cal, unless you just say, well, here's what it is, you don't get any practice with it until you get to calculus. And sometimes that's a little bit much, when you're trying to get all these concepts beaten into your brain and then you're struggling with absolute value. So you might be saying, well, is this exactly what Professor Ron says it is? So if we looked at this, we should be able to unravel this to get exactly that. And let's show that we can, because now this meets this criterion. This is a conjunction. And so the conjunction says that if we have this theorem, we can write this. So here our C is actually the 5. So now equivalently from the conjunction theorem, again, we're just going in circles, but I just want you to believe this. We get -5 less than or equal to x minus 3 less than or equal to 5. And now, of course, this is just a compound inequality, we can add 3 to all sides. So we add 3 to -5. So I'll write all of this out, in complete detail, even though I know you can do this in your head, but this just to make a point. So add 3 throughout. And then, of course, the -5 plus the 3 is the -2. The -3 and the 3 absorb. And then, of course, 5 plus 3 is 8. So that's exactly, I mean, you wouldn't have to do this again, but if you had a problem in WebAssign where they said, okay, do this, write the interval using an inequality with absolute value, you can apply these 2 steps here. And that way, I mean, you might look at it and just draw it. You could probably just draw this and just kind of eyeball it and say, oh, well, the distance, oh, I've got it, I can write it down. Certainly you could do that. But if you were working in the abstract or the numbers weren't very user-friendly, this technique will take care of that. Again, find the midpoint using the sum the left and right endpoint, divide by 2, take their average, all arithmetically, and then find half the distance between the left and right endpoint. And then that becomes basically the C. And of course, the midpoint becomes the point that you put here. So again, in calculus, sometimes the C gets used. You'll say X minus C in absolute value less than delta. For instance, you might have an expression like this in calculus where we have a new C. I mean, unfortunately, letters are used indiscriminately. You often in calculus have a notation like this where you say the distance, for instance, you'll say X is within delta of C. Here we say X is within 5 of 3. X is within 5 units of the number 3. X is within delta units of the number C. So these constructs are exactly alike. Now we just, we've changed up the letters a little bit. Now I would be saying C is 3 and delta is 5. So the idea here is the next time you see this, I don't want you to just be like, wow, what is this? Why do we even care? Again, many smart mathematicians came up with this notation when the calculus was discovered and everyone was trying to communicate. No one had even defined really what a function was. And then what did it mean to get close to a number? And so everybody just said everything in words. Well, excuse me, went down the wrong way. Never talk and try to drink. I need to stop talking. But the idea is that when you have people in France talking with people in America, writing letters, not using the internet, or mathematicians in Russia writing letters to people in America, there was no communication. So lots of European and German mathematicians got together, they defined what a function meant, and they started defining these tools to communicate mathematically. So now what you can see is we have a universal notation for mathematics that doesn't depend on the language you speak as far as your spoken language, kind of like music. So today we actually are very lucky to have a very user-friendly notation, which is the result of a lot of hard work of mathematicians that came before us. So now I want you to see that the construct is something that you can do and it's not mysterious at all. So very good. Again, absolute value is a very important function. It's just that you don't get a whole lot of use of it until you get to calculus, and then it's like maybe more than you want. Now, I wanted to do another BV technique and then also some application type problems with inequalities. So let's look at another one. So say we have x plus 1 is greater than 3x. Now, when we get to chapter 3 and we're doing theory of equations, there'll be another section where I'll assign some more inequalities to give you more practice, but the technique will always be the same. So we're going to say solve, solve in R. So when we think about this, we're like, okay, well, this is like the last problem that we did in the previous lecture, except well, it's actually the same. We didn't have a 0. And even in the proof we just did with the intuition, we didn't have a 0. So what we can do is say, okay, this is like 1.4, section 1.4. We want to put two items together and then combine them. So the first thing we're going to do is subtract the 3x from both sides. We really wouldn't have much luck trying to solve inequalities just by guess and check, there's some techniques in math that require us to do some intuitive type techniques where we guess and we check things like when you're going to be taking differential equations. But this is not a case where we want to do that. So say you're in section 1.4 and they say, subtract these, combine them, simplify. So again, the BV technique's not going to be useful here because we need things multiplied or divided so we can use the BV sign test. If we don't have that, sums and things don't work for us. We have to have everything in one unit. So the first thing we're going to do is get a common denominator. Notice here, that's just a 1, right? So we have an x plus 1 as the common denominator. So we have x, and then we have minus 3x times x plus 1. And we can do as much algebra as you like on these problems. As long as it's legitimate algebra, the inequality that results will be equivalent to the original one. It's just that in this form, we can't use BV. So now let's go ahead and do an equivalent, collect some terms. X minus 3x squared minus 3x divided by x plus 1 is greater than 0. And now, of course, we can go ahead and continue to combine terms. Very simple. So we have a negative 3x squared, and then we have an x minus a 3x, so that's minus 2x. Sometimes the simple algebra is the hardest because we don't always pay attention to simple arithmetic. But just remember, every step is important. And though unfortunately we don't like to admit that, we know it's important. Why did you put x plus 1? Oh, on top. Oh, okay. Now, in this case, notice everybody, when you have the common denominator, this is a 1. So 1 divides x plus 1 times. So then you have to multiply the negative 3x by the x plus 1. So when you cover this up, the x plus 1's absorbed and you're left with the negative 3x. So that's like compensating for now having a new denominator. So is that good with everybody? That's an excellent question. So it's kind of like saying 1/2 plus 1. Say, for instance, say we had this. Say we had 1/2 minus 3, something that looks a little bit like this. So the first thing we would want to do, excuse me, is get a common denominator. So we do 2. But notice there is no 2 here. So we say minus 3 times a 2. And so now when we do this, we have 1 minus 6 over 2. So this is just negative 5/2. So the idea that we do here is the same idea that we do here. So a lot of times, think about numbers, think about what you do with numbers. The letters, the variables use the same principles. Okay, excellent question. So now when I have this, we multiply and then we collect terms. Now you're thinking, when we look at this, it's like, okay, we got a bunch of negatives in here. So do you want all the negatives hanging out? Probably not. So let's try a little trick here. Let's multiply both sides of this inequality by -1 to get rid of the negative, and then of course reverse the inequality. So here, second step, we're going to multiply by the -1. So I'm going to say -1, and I'll just go ahead and write out this step because a lot of times this step gets lost when you don't write it out. Now, of course, if we multiply by a negative, what's going to happen to this? It's going to what? It's going to reverse, right? So we get this. So again, this is something that you can often do in one step. but since this is new, I want you to be good at it. So I want you to see what I'm doing. So if I multiply the inequality by -1, we know the inequality must reverse. And so all of these negatives are going to absorb. So I'll get 3x squared plus 2x divided by x plus 1 is less than 0. Of course, 0 times -1 is 0. But now these two are equivalent, but we don't have all the negatives hanging out, which makes it easier. Now, of course, we need the BVs. We already know that -1 is going to be a BV because this is undefined at -1. Now, again, we need to factor in the numerator to get these zeros. So let's just go ahead, if you like, and factor a 3x. So 3x, that'll give us an x. And then, of course, we take out the x, but then we'll have to pay for factoring the 3 because we don't have the 3 here. So divide the 2 by 3. And then we have an x plus 1 less than 0. So let's just go ahead and check this. 3x times x is 3x squared. 3x times 2/3, the 3's absorb, and we're left with 2x. Okay? So now we're at a point where it's kind of like we're doing complete factorization in college algebra. We can look by the zero product law to see, well, when would this fraction be 0? Well, of course, when x is 0, and also when x is negative 2/3. So if we factor this, we can now use the zero product that will easily give us the BVs. So now we say BVs. I did this problem, I got this from your book and then kind of made it up because it has a little bit of everything in it. And that way you can practice all of these techniques and get really good. And just remind yourself, multiplying by the negative, by anything negative, or dividing by negative when you're using an inequality will reverse the inequality. And that is something we do and we forget. We multiply by the negative, and we know in our minds that the inequality needs to reverse, but we don't do it because it's just easy to forget. Now let's write our BVs. 0, -2/3. And then, of course, where is it undefined? When x is -1, like a vertical asymptote. So -1. So now what we can do, and I factored this so it'll be easy to check the signs. So these are close together, so we'll be creative. Again, we've got to just spread them out so, you can see what you're doing. -1, -2/3, and then of course 0. So they're all kind of close together, but spread them out so you have plenty of room. And then of course we have 3x times x plus 2/3. And then we can be creative about picking test points that are easy to evaluate. That's the whole idea. When you've got something factored, create test points that are easy to use. So now, for instance, -1 here, I mean, we can just take any number less than -1, and we can just be real simple and just take a -5. You can use -2 or -100, not really going to matter. But here we want something that's in between these two numbers, so we can take a number that's more negative than 2, but not bigger than 3. So we could say -2.5 divided by 3. So that's just -5. Funny, same thing, -5/2 divided by 3. But I want to keep the denominator the same so it's easy to compute. So I'm going to leave it kind of in the awkward stage. So again, I don't want the numerator to be larger than 3, because then that's going to be less than -1, and that's no good. That's going to be over here. So I just pick a really convenient symbolic number that I know is between these two. That way you make your work easy. So this is what we call symbolic arithmetic. Now, someone chime in and give me an easy number that's right there that we don't have to work too hard. Somebody give me a real simple number that I can put right there. Anybody. Don't be shy. If it's wrong, I won't get mad. Do you want me to give you a hint? Okay, see what we got here. Oh, good, good, Jeremy. You get 100 points. So Jeremy said, let's just go ahead and use -1/3. And that's fine. Of course, we want a number that is larger than -2, which is -1, but it's also less than 0. So perfect. Excellent, Jeremy. And so now, what, if we want something bigger than 0, let's just take the additive inverse of that. So very good, everybody. So notice with this technique, we don't have to write an elaborate chart. All we have to do is just have easy test points so we can easily check the sign here. And we don't even care what the number is. We just want the sign. Okay, so for the -5, we'll just go into the first factor here. That will be negative. If we put in -5 here, the second factor is negative. And of course, -5 downstairs, we still get negative. 3 negatives, negative. 3 negatives, you multiply together, negative. But note, we want less than 0 right here. We want less than 0. That gets a check. Now, clearly, just to save a little bit of time, this is never going to be 0. So we're going to kick out, in this case, -2/3 and 0. And then, of course, undefined doesn't make any sense. So that gets an x2. So all of the BVs here get kicked out. Again, undefined doesn't help us at all. And then, of course, since we don't need equal to 0, we go ahead and get rid of these two. Now, let's use the -2.5/3. Okay, putting in a negative number for x, that's automatically negative. Now, the -2.5 is less than the 2. So when we add those together, that's negative. That's why I use the convenient notation there. And then, of course, here, notice we've got a number that's in absolute value here less than 1. So when we add this number to 1, that's still positive because, again, it's bigger than -1. So this symbolic computation is useful. So this is a plus. So a negative times a negative is plus, plus divided by plus is plus. So again, I don't care, and you shouldn't care what this number is. You just want the sign of the number and use the number line to kind of wage how big things are relative to others. Well, that's positive, no good. Now let's go over here to -1/3. Let's again test. We'll put in a negative number for x, that's negative. Now, of course, if we do the -1/3 and the 2/3, just like we had before, that's still positive because the 2 is bigger. And then, of course, the -1/3 plus the 1, again, that's positive. Now, this is good. Positive divided by positive is positive, times a negative, overall negative. Again, this is less than 0. That gets a check. And then, of course, the extremes are always the easiest. 5, again, we do the plus. The 5 here is a plus, and the 5 here is a plus. So this little sign test with the number line is so much easier than drawing an elaborate chart and then trying to find the exact number, which is a complete waste of time. We only want to do enough work to get us where we want to go. We can always think about other ideas, but inequalities come up all the time, especially in calculus. You need to know the sign of the first derivative. Is it increasing or decreasing? You need to know the sign of the second derivative because you need to understand the shape of the curve, the concavity. So doing this type of technique, you will do over and over and over and over in calculus. And honestly, you'll probably get tired of it. But now, just like we did with the proof, we follow the checks. We have a check here. So this says X lives, again, negative infinity to -1, using our little palette, math palette in WebAssign to -1. But of course, we don't include the -1, so we have a parenthesis. Okay, then we keep moving. We have X's here, X's. Okay, between -2/3 and 0, we have a check. So you can use your union symbol, connect it, and we'll have open, parenthesis, -2/3 up to 0. Now, after this, again, I didn't put my X over there, but that's no good either because it's positive. Now, let me just make a comment here that's very important. The BVs create these intervals, not the test points. Students will start to work and they'll start putting in the test points. No, the test points tell you what's going on in this particular region, defined or determined by the BVs. So again, you look for the checks and then you use the BVs to write the intervals. And so now when you look at this particular problem here, you see that in general, an inequality can be complicated to solve. And you could also see that if you just tried to do this by trial and error, that would basically be impossible. I'll have students say, well, how can I do this without a graphing calculator? I'll say many ways. Just remember, everybody, fancy calculators weren't around when all of this was invented. Calculators are just a helpful device. And when we need nice approximations, I did one yesterday with the Google calculator to get a nice calculus approximation. That's fine, but the hard work is done with pencil and paper. That's where the mastery is achieved. So when you think about solving inequalities other than just very simple ones that don't require this elaborate technique, you have to say, okay, I need to analyze this to figure out the BVs. That may or may not take a fair amount of time. And then once you have the BVs, again, maybe the most difficult part of the problem, you simply create a number line and choose test points. Because once you have the BVs, you've actually written the expression in a very convenient way. This convenient way sets up for the sign test. The sign test is easily executed when you have this form. You could see how this is utterly useless for a sign test, but the equivalent inequality of this is this, and this is extremely useful. So we look at this. What do we do in mathematics, ladies and gentlemen? We simply determine an alternate form of the given problem, be it an equation, be it an inequality, or whatever. We reduce it to a form that we can analyze. If you think about what you do in mathematics and you tell yourself, well, I don't get this, well, then think about what it is the problem is asking you to do. And then go back and think, well, what have we talked about and what have I done in my previous classes? So often, if you give yourself the time to process, you'll come up with an excellent solution. The only thing about math is that you have to practice enough so you feel competent. That's the toughest thing about math, just developing competence. Okay, now, so use this one as a good example for uh, find a similar problem or a similar way of thinking. Yes, exactly, exactly. So the idea is that this gives you a technique that you can use. And if you know other techniques that you've learned in other classes that you want to apply to this, that's fine. I just want to make sure that when you have a particular response, that you have some confidence. And notice there are many aspects to this. And so you may come about your BVs a little bit differently. Maybe you don't worry about the negative signs. I just know it's nicer to have fewer negative signs when you're trying to figure out plus or minus, right? Okay, so let's do another example of an inequality that's a word problem, so to speak. So I've got an example here. Let's see. I pulled these from your WebAssign. Let's do one about mileage. So here we go. This is just an example where they basically give you an inequality. So here, and then they say, pose a question about the particular expression that forms an inequality. So we're going to say that gas mileage, we'll say G for gas mileage, is given by 10 plus 1/2 V minus 1/100 V squared, where we're going to talk about V as being speed. So we'll say V lives here. That is between 10 and 65. So we can think of V as speed, say for instance, in miles per hour, if you like. And so what we want to do is solve the following problem. For what range of V is the gas mileage at least 14? So when we say something is at least 14, what we say in this particular case is we say, okay, it can be 14 or greater. At most means you would say less than or equal to 14, but at least we know we want the smallest gas mileage to be 14 miles per gallon, but we would like larger. And so now when you look at this particular problem, you're like, these are where the ranges have to fall for V. So we look at this inequality and see by using the BV technique, excuse me, we can then say, okay, where is this inequality satisfied and where does it intersect this, if it does at all? So we want to solve the inequality. Solve the inequality. So this is going to be a nice example where we can get rid of some of the unfortunate numbers and all the negatives. So we've got what? -1/100, get to use our theorems about inequalities, times V squared plus 1/2 V plus 10 is greater than or equal to 14. So we replace G with its definition. Now, just for ease of use here, this -1/100 makes it a little bit hard to use Professor Ron's AC lemma and makes it a little bit hard to use just in factoring in general. So what we're going to do is multiply by -100 to clear that out. So I'll go ahead and write this again so it's clear what we're doing. It's nice to go ahead and write it twice. That way you can see what's going on. And then you can go ahead and reverse the inequality. So here, reverse inequality. So I'll put that in parentheses where we say multiply by -100. Now, when we look at this, again, we can do this symbolically. So we have the negative. Again, notice the two negatives become the positive and the 100s go away. So that gives us a V squared. Again, the 100s absorb, the negative times the negative, positive. Now let's move to the next one. Here we're going to have negative 2 into negative 100 gives us a negative 50. So we have minus 50B. And then, again, easy numbers, 10 times a negative 100 gives us a negative 1,000. And then here at the end, we have 14 times a negative 100, which gives us a negative 1,400. So at least the numbers here are a lot more user-friendly. And then you're saying, okay, we got to do the BV technique. So we started with this inequality, and now we have this. So the next thing we need to do is move or add the 1,400 to both sides to get the 0 that we need, and then factor to find the BVs. So equivalently, V squared minus 50V. Now, of course, we're going to add the 1,400. So the 1,400 minus the 1,000 will be positive 400. So at least these numbers are easy. The ones that are easy, we can kind of verify. So basically here, adding, I'll just do a little subtext here, add the 1,400, add the 1,400. And that gives us the 0 and the 400. Now you can see that the numbers here work out really well. So we can do the AC. First, AC is just 1 times 400. But we want a negative 50, so we can just use 10 times 40 and put in 2 negatives. So this one fell out pretty easy. Sometimes you notice I've got to do more elaborate factoring because the numbers aren't as easy, but negative 50 is an easy number. Unfortunately, sometimes the AC method does require that you use prime factorizations and just redistribute the numbers. But here, this is good. So we can use a negative 10 and a negative 40. And then, of course, these two numbers sum to the negative 50. So the AC works really nicely here. Okay, so now we can, and then of course, you can factor by grouping, but this is just a leading coefficient of 1, so we can just go ahead and write it down. So we'll have V minus 10 and V minus 40. So the idea here is that when we look at this, again, we can think of the factoring by grouping, but we got the V squared, we got the positive 400 and the negative 50V. So now we're good. We can do the BVs. BVs. So we set the first factor to 0, we get a 10. And we set the second factor to 0 and we get a 40. So at least these are numbers that are falling in this interval. So our intuition now is saying that this is actually possible. So let's do our sign convention. So we have 10. And notice that's the lower limit. And then, of course, this upper limit here of 65, we just kind of remind ourselves, and then we've got a 40 over here. So this just kind of reminds us of the limits that we're having to work with in the V. So we're not going to go outside that. There would be no need to do that. It wouldn't make sense. So in this particular case, we don't even have to check over here, but for the 10 to 40, we can just do a 20. And then of course over here, if you like, we can just do a 50. So this is our universe, so to speak. We have a limited universe. And so now, if you like, I've already got it really right close to it, but I'll go ahead and put it right above here. So now we'll substitute 20. So we'll get positive. And then 20 here, we have a negative. So overall negative. So of course, less than 0 gets a check. And then of course, equal to 0 at 10 and equal to 0 at 40. Now, of course, if we look here, we just need to check the 50 because it is actually between 40 and 65. So that's something we need to check. So when we put in the 50, we get a plus. And the 50 here, we get a plus, overall plus. But positive means greater than 0, which is not what we want. So when we think about these word problems, this one wasn't so bad. We didn't have to come up with the inequality. The more complicated problem would be like if we were doing an optimization problem in calculus, or maybe a problem with a quadratic function where we have to come up with the actual function and then analyze it. That's a harder problem. But at least here we were given the formula for the gas mileage, and then we had to intuit the correct inequality from what was given to us and then solved by the BV technique. And so now this implies, because we've got our universe here, that the B will live between 10 and 40. And we are done. So again, it doesn't matter if you don't look at the universe here, you can just solve it for the whole real line and then restrict to what they give you here. So I think now you see that when it comes to working with inequalities, there's really no difference. The technique is with the signs. And if you're working with multiplicities of zeros, like we'll have with theory of equations, and you're working with other constructs that you see a lot, you can do less work. You know, you can use your absolute value. There are all kinds of ways to quickly solve inequalities that are simple. But when we have inequalities, one thing that we love quadratic equations because we can always solve a quadratic. We can always figure out the BVs, no problem. Maybe we have a quadratic that's never 0. That's even better, as long as we need a positive result. So just look through here and just see that all we're doing is applying the same technique, and use whatever techniques you already know and these ideas to amplify what you know. And I think you'll have the success you want with inequalities. Put in as many steps as you need. Check things to make sure that you abide by the theorems about multiplication by negatives, and you'll be good. And then, of course, finding the BV sets you up for the sign test. So the sign test is really a theoretical result based upon real numbers. We have really interesting sign conventions in real numbers. A negative times a negative is a positive. A positive times a negative is negative. Okay, a positive times a positive, that's just the set of positive real numbers. That seems obvious to us, but the real numbers have some particular attributes that are somewhat puzzling to non-STEM people. And so that's when you have to be very careful about the things that don't seem as intuitively obvious. Now, there are other examples in your WebAssign that you can work on. What I want to say something about now are functions. And we have, I've got, Thursday, I've got several conference sessions, so you are certainly welcome. I'll send out email invitations for those, as I always do. Now, when we did this last problem, you're thinking, well, that gas mileage formula, that Professor Ron, that was really a function, right? It's like a machine. You put in a V, and then you get an output. That is, you have an input that produces exactly one output. That's really what a function is. It's a well-working machine, kind of like your transmission in your vehicle. When it works, you input a particular position that is based on the dial on your vehicle. So you want to go forward, then you input D for drive. And fortunately, if it's working right, you will move forward. So you can think of your transmission as a function. And of course, we always like functions to work. And then, of course, when we define functions for problems that we're working on, we want to make sure that the function does exactly what we want it to do. Models in mathematics can be created, at whim. But we have to be scientists too and investigate and make sure that whatever we've created actually solves the problem. So often people will say, well, you're using the smoke and mirrors with the math. I don't believe it. Yeah, that's where we have to be really good at describing what we're doing. So this will be section 2.1, and this will be the fundamentals of functions. Now, what I have here, I've got some examples here that deal with the basics and how we work with functions in general. And of course, I'll have to say a little bit more about absolute value, my favorite function. But let's just recall a couple of things that you learned in your college algebra course. A relation is any set of ordered pairs. Now, in mathematics, we usually think of ordered pairs of numbers, but you could have ordered pairs of letters or symbols or whatever, depending on what type of mathematics you were doing. But we tend to think, at least in our realm, that we work with ordered pairs of numbers. So if we've got a set of ordered pairs, that's a relation. And we're thinking, well, that's what functions are, because we can plot functions. But what makes a relation into a function? So let's go ahead and write that down. Definition. And we'll say this, I'll give it a name. A function f, and that's usually the letter we use, even though we can use any letter we like. A function f is a relation such that, and in this particular case, we want to say, well, what does it mean about the ordered pairs? Such that if A, B as an ordered pair and AC as an ordered pair are elements of F. They're elements of F. This would imply that B equals C. So you're thinking, what is that? What is that? Well, ladies and gentlemen, that's basically the vertical line test. This is a way of writing it in terms of the ordered pairs of a relation. So what is this saying? Well, basically, you have an input here, A, and you have an output B, and here you have an output C. If we have a function, then exactly, we're saying this intuitively. Every input has exactly one output. So it would have to be the case, if this were indeed a function, that B and C would be equal. That is, the outputs would be equal. So we could say each input has exactly one output. So basically what we're thinking of is that the set of inputs corresponds to the first coordinates, or the x coordinates. The set of outputs corresponds to the second coordinates. Now, of course, we usually think of x's and y's, but maybe we call our inputs T and the output Z or whatever. It doesn't matter. But basically here, this is what we call, because if we were to plot all of these points, no 2 points would be aligned vertically. That would mean they had the same output. So this basically is the vertical line test. I mean, it's like when pictures don't prove anything. Pictures give us ideas. But I could draw a picture of a function and it may not even look like a function. You'll say, well, that doesn't satisfy the vertical line test. And I'm sorry. I'd say, well, I'm not Rembrandt. I'm not Rembrandt. I didn't mean for it to look that shabby. So we need a way of discussing what a function is that doesn't rely on a picture, because that's not a proof. We need a definition. And so if you think about plotting points of a function, you would not have an alignment, even though it might look like the function is approaching a vertical line. We try to draw our functions so that they imitate the correct disposition of those points. And sometimes, things approach vertical tangents and they almost look vertical, and we try to draw them so that they're at least convincing. So when you think about the set of inputs, we have another name for it. We call this the domain of F. Domain of F. When we think about the set of outputs, we call this the range of F. Now, what's interesting about functions is that you can create any function you want. Most of the functions that we deal with in this class are real valued functions of a real variable. But for instance, say you have a function H that you make up, maybe not even a very interesting function, that has 4 elements. You'd say it has 0, 1, square root of 2, 3, 1/2, 5, and we'll say it has the number pi that from geometry, pi square root 3. Now that's a pretty haphazard function, but it is a function. It is a set of ordered pairs, and every input has exactly one output. That is, when you look at 0, root 2, 1/2, none of the inputs is repeated. So you don't have this failing to hold. So then you say, okay, well, the domain of H would be the set of inputs. So we could say 0, root 2, 1/2, and pi in no particular order. And then you'd say, well, this is an interesting function because all the range elements are unique in the sense that we would look at this function and later on call it 1-to-1, but that'll come later when we review it. So we look at the set of outputs, 1, 3, 5, and the square root of 3. So this is what we call a discrete function. It has a finite number of elements. And maybe this would have no consequence for you, but maybe to someone else who was doing a little puzzle or something, this was an important function. Functions are very general, and the abstraction of the function is probably one of the most important concepts in all of mathematics, because the function is a way of communicating between spaces. And so we can transfer information. Those of you that want to become computer scientists and computer engineers, the concept of function in the C languages is imperative. The C languages are basically constructed mathematically. And so you move variables around with constructs called functions. So again, until the concept and definition of a function was actually written down, mathematicians had a really hard time communicating. And so again, like I said before, we enjoy all of these great definitions that were handed to us so we can do mathematics a lot more efficiently and hopefully more accurately, even though I don't think we compare to some of our predecessors who discovered and invented all of this. So how does this transfer to pre-calculus? In this class, we study, and I'll say we study real valued functions of a real variable. What does that mean? Well, for a function f, this means input is a subset, it's like a lazy U, is a subset of the real numbers. Maybe it's all reals, we don't know. And the output, which is the range, so I'll just say domain, and the output, which is the range, is also a subset of the real numbers. And so this means subset. So the domain set is contained in the real numbers. The range set is contained in the real numbers. So we say real valued function, that is the output is real, of a real variable, that is the input is real. When you study calculus, you study real valued functions of a real variable. And then you're thinking, oh, wow, okay, so all those formulas we wrote down in college algebra, those are real valued functions of a real variable. So let's look at an example. For instance, here's an example. Now you're thinking you could always write down a bunch of ordered pairs, but if they're an uncountable infinite number of inputs and outputs, then you need letters that will help you with that end. And that's where we talk about variables. So for instance, we could say that the input is X. We'll give it a variable name, and we could look at the function 7 minus X divided by 7 plus X. So when you look at this, you're thinking, okay, how does this and this match up? Well, it's the same thing, but when we look at this, there are an uncountable infinite number of inputs if we think of real valued function of a real variable. So we can say, this looks like this. All ordered pairs X, comma, 7 minus X, 7 plus X. And then we would say such that X is a real number. So that would be a way of writing this in terms of a set of ordered pairs. But we certainly couldn't write them all down. That would be impossible. And then you say, okay, well, X has to be a real number. Now the important part is that if we input a real number, the output must be a real number. And so when we analyze this function, we first say, okay, well, what is the domain? Well, I mean, let me just look at this. What is the domain? So we'll say domain of G. This would be very formally all real numbers X such that, and if we look at this, that would say, well, I want the output to be a real number. So I would need that X plus 7 does not equal 0. If I'm if I'm thinking that I want real input and real output, whatever input that I use, the output must be real. But I'm looking at this and saying, I could not make an input that would cause division by 0 because I don't know what that is. That's undefined. That's not a real output. So then I'll say, well, let me say a little bit more about this. Let me write it in a way that might give a little bit more information. Let me just subtract 7 from both sides. And so when you look at this, you're thinking, okay, the domain of G will be all real numbers except -7, because of course, -7 would render division by 0, and that's not real. So you're thinking, okay, that makes sense. If I've got a formula that has a fraction in it that's made up of a fraction, then I have to be careful if I state the domain that I do not cause division by 0. And so then I would say, in terms of intervals, I could say, well, -infinity to -7 union -7 to infinity. Now, of course, you might think, well, that's a little bit easier, but it's nice to write things in terms of intervals because that's a very, very efficient way to construct sets of real numbers. Now, when you look at this, you're thinking, okay, well, let's do a little bit more work with this. This has a lot of good information in it. So we can't always be so resolute with functions because they get more complicated and then we have to use some calculus. But what I've got here is just a couple of examples here. We're going to say a little bit more about this, but let's just do some computations. So let's just say G of 1/2. Okay, so we know 1/2 doesn't equal -7. So we can say, okay, well, this will be 7 minus 1/2. We're back to section 4. 7 plus 1/2. So this is what we call a compound or a complex fraction, a fraction of fractions, which you did in section 4. And so now the first thing we could do is we can say, go ahead and get common denominators upstairs and downstairs. So we have a 2. So again, the 2 times the 7, that'll be a 14. And then of course the -1. Do the same thing downstairs. We have a common denominator of 2. And then of course the 2 times the 7 will be a 14 plus the 1. Again, remember this is just like what we did in the warm-up. The 14 over 2 gives us the 7 in both cases. So when we reduce this, we get the original. And now we invert and multiply. But if you like, 14 minus 1 is just 13 over 2. And then, of course, this will just be 2 over 15 when we invert. And now, of course, the 2's absorb, and we get 13 over 15. So when you look at this example, you're like, okay, this is back to section 4 in chapter 1. It's the same thing. But maybe that was a 7 minus 1 over x. Okay, and Dr. Stewart threw in some letters. But it's the same construct. So now we're starting to see, I see why Professor Ron has us do all these crazy algebra problems that seem to go nowhere. This is the reason. Now what we want to do is think about, okay, well, what if we just input some variables? Maybe we did a composition. We'll talk about that later. Let's do this. Say we had G of x squared minus 7. Well, let's go back to section 4 again. So this is going to mean 7 minus x. So this is what we replace with x. So we have 7 minus x squared minus 7. And then, of course, downstairs, we'll have 7 plus x, where x squared minus 7 replaces x. So we have 7 plus x squared minus 7. So this isn't as hard as the first one because we don't have the fraction. So now we're going to distribute. So we have 7 minus x squared, and then minus minus plus 7. One of those nice attributes of real numbers, subtracting the additive inverse is plus. And then we have 7 plus x squared minus the 7. So now we see the 7's add, and we get 14 minus x squared in the numerator. And then in the denominator, the 7's absorb, and we get x squared. So the idea here is that the operations with functions basically are the fractional arithmetic and working with powers and things that we reviewed in section 3 and 4. Now, one thing I wanted to note here is when you think about this particular function and you think about, what the range could be, this is what I was talking about before. Sometimes functions are really complicated, and it's really kind of hard to figure out what the range is without using some calculus. But let's look at this. Let's just think about this intuitively. What is the range? And I'm only going to think about doing this when it's possible to do the problem algebraically. So we're going to say let's just let C be some real number. So if we just took any real number, would it be possible to find an x that would input to give us C? So then we'll say equivalently, C equals our function 7 minus x divided by 7 plus x. So the idea is, would it be possible to have an input that would give us C if C were any real number? And if not, would we know which real number we could never hit? So this is simple enough that we can solve it. So let's go ahead and cross multiply. So this is just a little thinking outside of the box. So we'll have C times 7 plus x equals 7 minus x. And let's collect all the x's. So we have 7c plus xc equals 7 minus x. So let's get all of our x's on one side, all the terms with x's. So take these over here. So we have xc plus x. So we take care of that one and that one. And then take the non-x terms on the other side. So we have 7 minus 7c. Okay? So now we can factor. So we have x times c plus 1. And then, of course, we can factor this. This will be a 7 times 1 minus c. And now we can divide by c plus 1. Okay. Now you're thinking, well, Professor Ron, let me move this down for you. Here's where we started. So when we think about this and we choose some real number, again, this is only going to be the case when we can actually do this, ladies and gentlemen. I'm not going to say, well, what's the range, and not give you the tools to do it. But you can look here to say that if we take a particular real number C, this would be the formula for the input. So basically, I'm giving you functions in this case that are one-to-one. But now you look at this and say, okay, if I take any value of C, that'll give me the corresponding value of X. But note, C could never be -1. Because of course, if C were -1, this is undefined, so the x would not exist. So when we look at this particular function, 7 minus x divided by 7 plus x, -1 would never be in the range. And we don't need any fancy machinery to determine that, because we have a particular function of a certain caliber that allows us to do this algebra. So this would imply C can never be -1. That is, if we're thinking of hitting -1 in the real line as a range element, that wouldn't happen. So now this would imply that the range, again, when we can do it, the range of G will be all Y, we'll just give it another letter, Y element of R, such that Y does not equal -1. So then you could say, well, how could we write that as an interval? Well, we'll just throw out the -1 like we threw out the -7 here. So we'd say -infinity to -1 union -1 to infinity. Now, of course, there'll be times when we're dealing with functions where intuitively we will kind of know what the output is. But here's an interesting situation, because when you look at this function as a rational expression, you see that the horizontal asymptote is actually y equals -1. And we'll say more about that. And that is indeed what's going on. The function does not meet the horizontal asymptote. It does not cross it. And so this is a way of looking at that. I mean, students will say, oh, but you know, sometimes, Professor Ron, it does happen. And I'll say, you're exactly right. So you can't make these blanket sweeping generalizations about mathematics, because in general, they're not true. So when it comes to finding the range, that in general is a difficult problem. Even finding a domain can be difficult if the function has certain qualities that make it hard to analyze. So the key here is think about what we're going to be focusing on in this class, and always in your mind think, okay, if I have a real input, do I get a real output? And let that be the way you judge determining what the domain is, and then judge determining what the range is when you can do it. So that's just kind of food to process, so to speak. Now, I wanted to say a couple of things about some other examples. First, let me just go ahead and throw in a little bit of absolute value, and then I want to do another let's see, where is that? Another domain calculation. So here's another example, just to kind of throw in some more absolute value. So we have f of x equals the absolute value of x divided by x. Now, if we look at this function and think about it, well, you'll say, that's interesting. That's an interesting function. And then you're thinking, well, it doesn't look too complicated. And it really isn't. So before, I just want to have you look at this and say, well, could we break this down into two pieces? You know, functions don't always have to be given in terms of one expression. Maybe it's a function in pieces. So when we look at this, we could say, well, the absolute value of x is x when x is non-negative. But first of all, we see that we have an x in the denominator. And of course, x could never be 0. That's not defined. So we clearly know the domain is all real numbers except 0. That's obvious. So we could go ahead and just say domain of f will be all real numbers except 0. That's clear. That's what you did in your college algebra class. So now we could say, okay, well, this will be x over x, which is 1 when x is positive, because absolute value of x is x when x is a positive number, but we don't consider 0 for obvious reasons. And then we'd say, well, this is the additive inverse of x divided by x, which is -1 when x is less than 0. So you think about this particular problem and you say, okay, well, it's just basically x over x, and x divided by x is 1. Well, since we have the absolute value, the actual output of the function changes. So we have an output that's 1 for some x's, and we have an output that's -1 for other x's. And what we can see is this is clearly not 1-to-1. There are only two outputs for all these uncountably infinite number of real numbers. And so then you say, okay, well, that's an easy graph. We can always graph the simple functions. You know how to graph square roots and absolute value and the cubic function and the square. That was the family of functions you learned about in college algebra. And so if you thought of 1 and -1, here, let me put the -1 on the other side. Oh, this is a new eraser. I have to get it going. There we go. So I'll put the -1 here. So we would have no value is 0, so we'd have a circle and then 1. And then, of course, a circle at -1 and then negative. So this is a very interesting function. The graph in this case consists of two pieces, 1 and -1. And then at 0, there's a circle. There's no definition. So it's a function with a discontinuity. And then you'll say it's a function with a jump discontinuity, in the sense that the function doesn't become infinite, but if you're going down here, then you're going to have to fly or something to get up to here. So there's a gap in the function. We would say this function is not continuous. And that's going to be something that you do more with in calculus. So when you think about teleportation. That's even better. Thank you. Yes, I'm like, yeah, you become a helicopter. Absolutely, teleportation. You all are great. You're going to do a lot for my humor, which is obviously severely lacking. My students always say, "Don't quit the day job, Professor Ron." Yeah, that's why I do math and music, because I'm better at doing those than stand up. So what we can see here is that when we look at this function, it is really, really different. And now we see the range just consists of two numbers. So now this implies that the range of f is just what? 1 and -1. How interesting. Obviously, we have uncountable infinite number of inputs as long as we avoid 0. And then the outputs, they just hover between 1 and -1. That's it. So not all functions will be that difficult to analyze. Some functions will be fairly simple and fairly interesting. So now you can see how this absolute value function is really, really important. And as we need, ladies and gentlemen, I'll do more examples with the absolute value to give us more of the properties. But I don't want to beat you up to the point that you start to get kind of loopy about the absolute value. Now, what I want to do is another domain problem. So let's look at this, and then we'll talk about a difference quotient. Again, remember with functions, remember everything you learned in college algebra, and then think about some of the new ideas I've introduced today. just to kind of build your foundation. So say that we have, and in this case, I'm just going to ask you for the domain. We have g of x is the square root of x divided by 8x squared plus 7x minus 1. Okay, so here's a relatively interesting function, a little bit more complicated than this one. I don't know, maybe you thought this one was complicated because it had the absolute value in it, but a very nice function for calculus. So don't forget this when you get to calculus. You can say, oh, here's a nice discontinuous function that's bounded. You know, you can use some fancy words and impress your calculus 1 professor. So here's what we want to do. Compute domain of G. Now, when you look at this, there's certain restrictions that we haven't talked about before. Square roots are important restrictions because we know we can get lots of imaginary numbers when we take square roots of negative numbers, but we want the output to be real. So first, in this computation number 1, we see that x must be non-negative. That is, if this square root function is going to give us real output, the only inputs can be non-negative. That is either 0 or positive numbers. And so there's a restriction right there that we must observe. And then two, another restriction, which we're already really good at doing, is that we don't want to divide by 0. So we can say 8x squared plus 7x minus 1 does not equal 0. So if we're going to compute the domain of this function, both of these constructs here must be observed. This one's good. We're pretty much done with that. There's nothing more that we can do to simplify that. The argument of the radical is very easy. But here we're thinking, well, this is, again, what Professor Ron's lemma. So let's look at this. So we have AC equals 8 times the negative 1. Well, that was a jackpot. Obviously, 8 plus negative 1 equals 7, so that was easy. So let's see, we've got 8x squared plus 8x minus x minus 1, not equal to 0. So we have 8x, we can factor the 8x, and that'll leave us an x plus a 1. And then, of course, here we can factor a negative 1. And that leaves us an x plus 1. And this should be non-zero. So now we have x plus 1 times 8x minus 1, not equal to 0. Now, of course, this is why we did what we did the first week. We just used the 0 product. So we have x not equal to negative 1, and then adding 1 to both sides, dividing by 8, x not equal to 1/8. Now, of course, this is an and here. Now, first, when we observe this number is negative 1. Okay, so we don't even care about that. I mean, there's nothing to worry about here. X must be non-negative. So this is not going to impact the domain at all anyways. Negative numbers have no impact on this function. So that's of no consequence to us. But this number here is positive. And so we would need to exclude this number in the statement of our domain. So now we'll say we start at 0, we approach 1/8, we omit 1/8, and then anything greater than 1/8. So this implies, using 1 and 2, that x would live between, well, we've got 0 to 1/8, and then union 1/8 to infinity. Now, when you think about this, again, this is not a hard problem. The only thing is that you have to abide by what the mathematics of the function is telling us. That is, when we look at this problem, we automatically have two ideas that we must consider. We didn't have to do a lot of work for the numerator. We did a little extra work for the denominator. And then combining the two gives us the domain. So there often will be numbers that turn up in a problem. It doesn't mean that they're unimportant. It's just that they have no impact on the solution. It's kind of like doing a the fraction of work problem, and we get the hours that K works to be less than 0. Well, I mean, mathematically, that does solve the equation, but it has no impact on the problem because we would not have a time commitment to be less than 0. So again, the mathematics from the equations can give us ideas that are correct theoretically, but do they actually solve the problem when we consider other aspects that are given in the hypothesis? So this is a good example. Now, there's a problem that I want to do with a difference quotient. And you did some of those. Again, what we're doing today is just a lot of algebra. So when you think about the algebra you did in 1.3 and 1.4, you see that it's really function algebra. So functions, like I said before, give us great ways to communicate, and they give us ways to analyze things in a more mathematical sense. So for instance, when we take calculus, we might have functions like this. I love rational functions. They give you so much nice work in terms of algebra. And they're fun to analyze. I know you remember these from college algebra. Say we have a function x divided by x plus 1. You could think about the domain and range. I've already taught you how to do that. But what we want to do is compute. Again, of course, if we compute this difference quotient, we know that x would never be -1 because it's undefined. And so again, you can think about that. We want to compute what we call a difference quotient. And so we're going to have an a plus h. And then, of course, in calculus, sometimes you have an x plus delta x. You have an a plus delta x. H and delta x can be interchangeable. Doesn't really matter. Dr. Larson uses both in his calculus book. And then Dr. Stewart, he also wrote a calculus book. But I like the Larson book, but the Stewart book is great too, that I used as a graduate student at Texas A&M. So they're good things about both. Now, when we compute this, we call this the difference quotient. And this is involved in the definition, one of the definitions of a derivative. So right now, what we want to do is just look at the algebra construction. So now we have f of a. Let me get my plus h. So we have f of a plus h minus f of a divided by h. Now, of course, this 1 over h is just kind of a thorn in our side. So first what we'll do is we'll just put the 1 over h to the side. And of course, hopefully, we'll keep our fingers crossed that it will absorb. So we'll just do the 1 over h here to the side because that's not where a lot of the action is going on. And let's do f of a plus h. So we're going to replace x with a plus h. So we have a plus h. And then downstairs we have a plus h plus a 1. So again, remember, what does the function notation mean? We replace x with a plus h. So we get a plus h divided by a plus h plus 1. So now you, again, rational functions. Why did I have you do 1.4? Well, this is why. Now minus, now we replace x with a. So we have a and then a plus 1. So this is correct, but in a calculus sense, it's not reduced. It's not simplified. So this is why you would say, well, what does simplify mean? Well, it's a lot simpler than this. So that means that we want to combine things algebraically and then see if certain terms absorb to make the process of analyzing easier. So now we have 1 over h. And then downstairs, we just need a common denominator. So we have two factors, a plus h plus 1 times a plus 1. So when we do our common denominator, it's like the least common denominator, and we have a distinct copy of each factor. And so now notice the a plus h does not have the a plus 1 in the denominator. So we say a plus h times a plus 1. I'll extend this over a little bit. And now, of course, the a here does not have the a plus h plus 1 in the denominator. So we have minus a times a plus h plus a 1. So the idea here is that we think of this like the least common denominator method. Even though we have a lot of letters running around, it's no different from numbers. We just have distinct copies of everything. So now when we try to go backwards, we can see that this would absorb and give us this term. And then in this particular case, the a plus 1s would absorb and give us that term. So this is completely equivalent. So now we have 1 over h. If you like, we'll just be court reporters, and we'll go ahead and write the a plus h plus 1 times the a plus 1. That's kind of stagnant right now. And now we want to multiply the numerator terms. So we'll have a times a, which is a squared, and then a times 1, which is a, and then h times a, we'll just write that in alphabetical order, ah, and then h times 1 plus h. So that's just the distributive law. And now we can multiply each of these terms in the parentheses by minus a. So we'll have minus a squared, and then minus a times h. So that'll be minus ah, and then minus a times 1 minus a. Again, very straightforward algebra. And then you're thinking, well, why are we doing this? Well, I just told you this will be something you'll do with the definition of derivative. So now what we can do is just see that we get things that absorb. So these absorb the a and the a squared, or the a squared and the negative a squared. And then, of course, the a's absorb here. So this is a way of just checking them off. And then, of course, the AHs. Now, of course, you can and what I've done here, and just to make it a little bit easier, is I'll go ahead and write this down. This is a squared, just go ahead and combine the minus a squared plus a minus a plus ah minus ah plus the h. So I just put everything together and showed you how we redistribute, commute things, and then redistribute the parentheses so we get a bunch of zeros like I have here. So just think of it that way, and it's easier without having to skip any steps. And now all of these are 0. So this gives you 1 over h times, and the only thing that survives here is the h. So we have h, a plus h plus 1 times a plus 1. So the idea here is that there is hope for this function, because now we see the h's absorb, and this is actually much simpler and kind of the goal of this problem. That is, we want the numerator to get smaller, get closer to 0 quicker than the h does if we want the tangent line to exist there. So this just gives us 1, and then we have a plus h plus 1 times a plus 1. So So when you look at this, again, this is a computation that may seem a little bit off the beaten path, but the idea is, like I said before, the difference quotient is how we construct one of the definitions of the derivative, and where we would know that we could construct tangent lines to the graph of a function. And so now, again, just look at this as basic function algebra. This is called the difference quotient. And all we do is apply the function algebra and then reduce algebraically. So now you can see why we did 1.3 and 1.4. Now, there are other examples that you're going to see in section 2.1 that'll just give you some practice substituting numbers into functions and working with domains and just working with function algebra like we've done today. So again, you may find a lot of it to be fairly routine, but what I want you to do is think about the function as an abstraction that's important to us because it allows us to communicate between spaces. And the function itself is just like a well-working machine. We have one input, we get one output. It doesn't break down on us. Now, of course, we can break down when we work with the functions and write things that are incorrect. But the main thing is to use what you already know about functions and add to that. And then, of course, next week, we will put in some ideas about function transformations, compositions, one-to-one, and quadratic functions, which will be like mind blown. You know, all of this college algebra stuff will come washing back to us. And so that'll be the culmination of the items for the first test. But I appreciate your attendance today, and I will be sending out invitations for the conference hours today. We'll have one at 11:45. There'll be another one at 3, and then of course one at 7. I don't know what I was thinking about Thursday, but I think Thursday's just a good time, just kind of like Monday. I have an evening conference session to give you extra time to come in and ask questions. So again, there will be invitations in your email about that. So look for that. And let me check here. I always have to check the chat. It says, do you like the Spivak book? Yes, Spivak is a classic. That is a definite classic. I'm a Walter Rudin fan, Rudin's Principles of Mathematical Analysis, and I'm certainly an Apostle fan, but Spivak has written a classic, absolutely. It is a tremendous book. When I taught more honors courses, I would try to bring in some of those classic texts, and I could get away with it. But what I like to do now is focus on the standard textbooks in analysis like Larson Calculus and Stewart Precal, because they give you all of the great ideas from these great texts, but I think they give it in a way that makes it a little bit more user friendly. But yes, Spivak is a classic. There's so many great books out there. I know that you all are kids of the computer generation, but there are so many wonderful books. So you should check online. Lots of times you can get a copy from Dover for next to nothing, or you can find a free PDF of books. So just like you have your ebook for your pre-calculus book. Okay, so everybody, thank you for your attendance today. And if I see you, I'm sure I'll see some of you at the conference hours. And then, of course, continue to send your WebAssign messages and email messages. And of course, I'll get back with you. I wish you well as you continue to study. And please stay warm today because, you know, Mother Nature is playing tricks on us. But everybody have a great day, and I'll see you soon. Take care. Bye, everyone.